I'm in the process of switching maybe from Doceri to do my recordings to Cast, or I think it's called Screencast-O-Matic. So we'll see what we think in case this looks a little bit different. But we are finally to the end of the semester, and I want to spend just a little bit of time on talking about gases. Gases are so cool, and just without the numbers part of kind of working gas problems, a lot of this stuff totally makes sense. Let's see what you think. So for instance, gases are compressible. And what I mean, compress means to squeeze. So you can squeeze gases down. So for instance, let's see if my little pointer works here. Over here, we see that we're going to, how do I say this? This plunger right here moves up and down. And these are gas particles. You can kind of tell they're gas particles. Can you kind of see the swish? They're like moving. Remember that gases have a lot of KE. What does KE stand for? Kinetic energy. So they're totally moving around. There's a lot of space between them. They are compressible. So here we're moving the plunger down. We have the same number of particles on either side. Okay, so that's what gases do. Now liquids, if you were to try to compress them, you know, you try to move the plunger down, they don't have all the space between them, so they are not compressible. So gases are so cool. What else we got? Let's see. Gases will expand to fill the entire container. Is that not cool or what? And you totally know that. I have an example here. So like these kind of look like fireflies, don't they? So these are gas particles again. Now, if we were to have this jar, for instance, and wait, should I say, we were to have these particles, 1, 2, 3, 4, 5, 6, 7, 8, these 8 particles in this jar, what would happen if I take that jar and I double the volume? Well, those 8 particles would fill the entire volume. I think that is so cool. So they fill their entire volume, and one of the things that we said earlier was they take on the shape of their container. What else we got? Oh, gases have indefinite. Indefinite means like, I don't know what their density is. They have indefinite densities. Now density, remember we use the symbol rho, that's density, is equal to mass divided by volume. So the thing about it is you could have a certain mass is fixed of you know, oxygen molecules, oxygen gas molecules, but you can monkey around with its volume and you can have an assortment of densities. That's what I mean. So let's see, this third one here should do that for us, see what it does. Yeah, so what this is saying is, now this is kind of strange. Of course, you would tell me that, you know, your pop is a liquid, right? If you were to take all your liquid, the liquid particles, and convert them to a gas, 1 can of soda would be equal to, now this would be normal atmospheric temperatures and pressure, would be equal to 1,700 cans of gaseous pop. Does that make sense? I think that's kind of a strange sort of thing. What else we got? Actually, I wonder if, yeah. That actually, the pop, taking 1 can of pop and making it into 1,700 cans of gaseous pop, that's kind of what this is that gas densities are low compared to those of liquids. Let's see, what else do I have here? Gases want to form a homogeneous mixture. Now we've talked about mixtures. Mixtures are 2 or more different substances that are combined together. And if you have gases, what's a homogeneous mixture? It means it's the same throughout. So here's an example here. If we take, this says there's nothing in this gas cylinder. And if we were to take CO2, and to the CO2 we were going to add argon. So the CO2 is blue, the argon is pink. If you give it enough time, then can you see where this is a homogeneous mixture? Homogeneous mixture here. It's the same throughout. Let's see, what else do we got? I mean, that makes sense because those gas particles are totally moving. They have a lot of kinetic energy. They're going to randomly go and make a uniform mixture. Let's see. And then the last thing I need to talk about, and we will be doing some numbers with the pressure. So the symbol for pressure is P. So the pressure, gases exert a pressure on the walls of their container. And this is what kind of goes along with this. So the gas particles, if I were to go ahead and, well, I guess on purpose, there's no wall containers to this. Okay, but can you see where those particles are bumping up against everything, including the walls of the container, creating a pressure? And we'll be talking more about pressure. So when we talk about the pressure of a gas, that's because, like the slide says, it's the collision of the gas particles against the container or against anything. Now, this is kind of like the wide open air. As we're walking around, of course, most of the gas we're bumping into is what? Nitrogen gas. And they are pounding up against us with a pressure of about, what is it, about 13 pounds per square inch, 13 psi. So there you go.